Okay, so let's start the lesson for today. For today, we will study the topic of neural machine translation, which is one topic in the um, natural language processing part. Okay, so for today, we have three parts. In the first part, we will discuss the introduction to machine translation. In the second part, we discussed the neural machine translation. So, I mean the translation model that use neural network, right? And in the third part, we will discuss the attention mechanism, which is one of the most powerful mechanism we apply to the neural network for natural language processing at the moment. Okay, so let's start with the first part on the introduction to machine translation. So machine translation, I believe that you have been using Google Translate. I mean, in the recent year, right? In Google Translate, you can choose the source language and then the target language, and then you can have the input in the source language, and then the Google Translation will translate automatically the sentence input for you to the language in the target, right? So in the recent years, the quality, the performance of the Google Translation is becoming quite um, uh, powerful, and I mean that the quality is becoming good enough so that you may see a big improvement in terms of the performance of the translation model. And this big performance gain was in fact uh, from the application of neural network in training machine translation model, right? Okay, so the machine translation task is the operation of translating a sentence, let's say the sentence X from one language called the source language into a sentence Y in another language called the target language. So you see one example we have in the slide here is the one sentence in the French language to be translated into the sentence in English, right? Okay, the history of machine translation was back in the uh, 90, 50, around a few a few a few decade ago, right? And it's quite early. That's a few decade when we have the computer, right? So the first machine translation was the model that translates the language from Russian to English, and it is a demand from the Cold War between the Russian and I mean other um, uh, from Russian and the other country, right? And for this translation system, it is mainly Ruby, and it uses a dictionary actually to map the Russian word to English word, right? So like the dictionary you have from English to Vietnamese, for example, and that translation system was using that dictionary. It has the mapping from Russian word to English, and then they combine with a lot of rule to make the translation to be as fluent as the normal human translation, right? If you want to see the demonstration of that translation system, you can click on the YouTube link on the slide. Okay, so here is common architecture of a basic rule-based translation system. You need to translate the from the source language to the target language, and what you do is you need to analyze the source language sentence, and then you also do the then from that you do the generation of the target language, and the transformation from the source to the target could be done in 3 levels. The first level is the direct translation from the source word to the target word, and then you do the syntactic transfer, and then you do the semantic transfer to make that translation as fluent as the human translation, right? Okay, so it consists of the 3 steps, 3 big steps. It consists of it's the analysis state, transfer state, and synthesis state. So analysis state is to analyze the source sentence, to understand the source sentence. For example, you do the morphological analysis, lexical analysis, sentence and word segmentation, right? And from that analysis, you go to the second step of transferring the source to the target. For example, you do the lexicographic transfer, right? To transfer, the word by word, for example, and then you do a structure transfer to make the grammar become you make the structure transfer, and here we use the source target transfer rule, right? And then to make the translation to be fluent, you do the synthesis to actually compose the target sentence. And here we do morphological generation in order to make the translation to be grammatically corrected, and also semantically corrected, right? So the rule-based system have a lot of disadvantages, and it require a lot of manual handling and human efforts. For example, you need to have a mapping dictionary from the source to the destination language, right? The target language, right? And you need a transformation rule, so that's the lexical rule, the structure rule, right? And also the morphological rule, right? So all of these are manual tasks, and it's require a lot of efforts to maintain such mapping and such transformation and morphological rule. And one important thing to remember about this approach is the overall quality of the translation system is not as good as the human translation. It have a low quality than the normal human translation, right? Despite a lot of efforts into these methods. So the most powerful translation system beyond this method cannot achieve the performance, achieve a good performance as comparison to the human translation, right? Okay, so then after the rule-based translation, researchers start working on the second approach, namely statistical machine translation, and this approach was popular in the 1990 and 2010, in that period. So for this approach, the model tried to learn a probabilistic model from the data. So actually, the objective of the model is to find the best sentence in the target language, and this is the best sentence correspond for the input sentence in the source language, right? So here is a zero, diagram for that statistical machine translation system. You have the parallel text, which is a collection of a sentence pair in a source language, and then the corresponding translation in the target language, right? And from that, parallel text, we do statistical analysis and come up with the translation model, which is the probability of source sentence if we know the target sentence, right? And we have the source sentence, and from that we do statistical analysis, and we can build a language model for the source text, which is the probability of having that sentence in that language, right? And we, from the translation model and the language model, we can apply the biased model to have decoding algorithm to be able to actually to find out the argument that maximize the probability, the joint probability of having the source sentence if we know the target sentence, and the probability of that target sentence, right? Okay, so the question is, we should find a way to model the probability of having the source sentence if we know the target sentence, right? And one of the way to model that probability is to for example, here we to add the alignment information into the translation. So we actually match a word in the source sentence with the word in the target sentence, and the matching here is an alignment vector, right? So basically, in order to model that probability, we add one more information to the data set, which is the alignment vector for every parallel sentence pair, right? So for example, here is the alignment vector. We have source sentence, we have the target sentence, and we have the alignment of the word in the source to the word to the word in the target language, right? So actually we can, by having that alignment vector, we can model the probability here to be the probability of having the source sentence and the specific alignment if we know the target sentence, right? So this is one way to modeling the probability for that statistical machine translation. Okay. So for the statistical machine translation approach, the system following this method, the approach are very complex, and it contains many small independent model, so it's still not as efficient as human, and it still requires a lot of manual handling and human efforts, such as the feature engineering step, and require external resources, right, to actually, for example, to build the alignment vector for every parallel sentence pair, right? And also the maintenance costs are very high for this approach, and we cannot reuse the effort we did for a specific sentence pair for switching to another language pair, right? Okay, so here is a figure that describes the progress in machine translation. Let's see. Okay, we have the timeline in the x axis, and we have the performance of the machine translation system here. So you see, I mean, here we have some system which was in the rule-based process, and we have some system that follow the statistical approaches, right? And here in 2014, we start building the neural machine translation system, and from that start, nowadays we can have the machine translation model that actually has a competitive performance as a human translation. Okay, so do I have any question for the first brief introduction to machine translation? Any question? Okay. So if you have no question, then I suggest we can stop for 5 minutes. Then we go to the next part of the lesson. Okay. Okay, so let's continue the lesson with the discussion on neural machine translation. Neural machine translation is defined as the approach of modeling the entire machine translation process through one big artificial neural network. Right? This is something defined in the ACL conference in 2016, right? Okay, so one common approach to do neural machine translation is to apply the sequence-to-sequence model. So in that sequence-to-sequence model, you have two. You have two small components in the network. You have one encoder and one decoder. So in that encoder, you use, for example, one recurrent neural network to actually generate the encoding information of the source sentence, mapping the input sentence into one representation in the high-dimensional vector. Let's say it's an embedding vector that encodes the information of the input sentence, right? And then in the sequence-to-sequence model, you have a second component, namely the decoder. And the decoder could be also another recurrent neural network that actually takes the inputs, is the embedding information, which is the output of the encoder. And from that, you generate the target sentence, right? And here, the target sentence is actually the translation of the input sentence, right? So the sequence-to-sequence model can be used for many other problems besides neural machine translation. You can use sequence-to-sequence model for text summarization, for example, to compress a long text to be a shorter text, right? Sequence-to-sequence model can also be applied in conversation, such as to build, automatic chatbot that can give the answer. Not the answer, but gives the, that can generate a conversation when you talk to the chatbot, right? You write something and then the chatbot will reply you the, it could be the answer or it could be the question, depending on the input received from the side, right? The sequence-to-sequence model can also be used for code generation. For example, you can think about the scenario where instead of writing the code by yourself, you can just say, okay, I want to do something like this by human languages, and then you have the code generation model that can actually translate that natural language into the Python code, for example. Okay, so this is not, futuristic, imagination. This is actually he actually implemented recently, and you can see the demo on the internet or through the YouTube website to see the models that can actually doing the code generation. So for that model, they use a lot of code writing channels in some code writing website, and then from that data they have a lot of data sets consist of pair of a pair of natural language problem, and then the solution for that that problem, and they train the model for that. And then at the end you have the model that was so good, so that it can actually generate the correct, Python code for a specific, requirement in the natural language. So it's quite surprising that we come up with that model recently. Okay. Okay, so if we use the neural machines, neural network for machine translation, then the network could be like this. It's encode second-to-second model. So you have the first RNN, which is encoder RNN that taking the input, taking the source stack as the input, right? You need to use RNN because the length of the input may be vary, so that's why we use the RNN here. Okay, so for this encoder RNN, so each step will accept one token in the source sentence, right? And at the end of the encoder RNN, it will produce an encoding of the source sentence, which is a hidden state in the RNN, for example, right? This hidden state captures the information from not only the last token, but also all of the information from the previous token. That is what we learn when we study about the RNN network, right? Okay, so starting from that encoding information, we can put the encoding into the into a second RNN, which is a decoder, right? So the decoder is a language model that generates the target sentence, and the target sentence is generated conditionally based on the encoding we learn from the encoder RNN, right? Okay, so in order to start the generation of the token in the target language, we can use a specific token saying let's start, right? And then that's a specific token combined with the encoding information generated from the encoder RNN, and then the decoder start learning, and it can generate the first token in the target language, and then we use that token to be the input in the next step, right? And then we fetch into the decoder again, and then it will generate the second token, and then again, and then we can generate the entire target sentence in the target language, right? And we will stop the generation if we receive a specific token saying it's the end of the sentence, right? So here for every step we will take the output, which is a token that have the max probability, right? Okay. Okay, so as I said, the machine translation here is considered as a conditional language model, right? Because we predicting words not only based on the context of the surrounding the previous word, but also based on additional condition, right? So now, I mean the common the normal language modeling does predict the word based on the context of the surrounding word. But for conditional language model, the prediction is based on additional condition from the source sentence, right? So different embedding here will generate a different sentence in the target output, right? Okay, so here we see if you write the probability formulation, it's a probability of having y if we know x equal to probability of having the first token in the target sentence if we know x, and then the second token if we know x and we already generate the first token, and then the probability we have third token if we already generate the first, the second token, and if we know the embedding of the input token, input sentence, right? So this is a conditional language model. If we remove the if part here, then we have conventional language model, right? Just predicting a word based on the context of previous word, right? Okay. So for the training the sequence-to-sequence model, we need to have a sentence pair. We need to have a collection of sentence pair where each pair consists of one sentence in the source language and the corresponding sentence in the target language, right? And we use this sentence pair as the training data for the model. We can use that specific token to say the starting of the target sentence, let's say, right? And then we can fetch that sentence pair into the sequence-to-sequence model, right? And then for every output of the decoder INN, we actually compute the loss, which is a negative log probability of the corresponding token, right? For example, here at the first step, it is a negative log probability of the token, and for the n, it's a negative log probability of the n token, and it's a specific, the special token marking the n of the target sentence, right? And by having that negative log probability here, we can actually doing the average over all the negative log probability for every token, right? And then we have the loss value, and then by using the loss value here, we can do a normal backpropagation to actually update the weight of the sequence-to-sequence model, right? So remember that for this model, we have two specific components, the encoder and the decoder. But for the training here, we actually optimize this, the two encoder decoder network as a single system. So we consider them as a big neural network, and we do the backpropagation from the end to the start, right? So it's operate end to end. We optimize the weight of the bot to RNN network simultaneously, right? Okay. Okay, so in our example, when we decode the target sentence, right? I show you that we taking the arc marks at every step, right? So for example, when we first generating the first token, we take the arc mark, right? To see what is the most probability, the token have the most probability, right? And then for the second token, we also we also choose the token that have the most probability, right? Okay, so by taking the argmax at every step, we actually doing a greedy decoding, right? So for the greedy decoding, if we make a mistake at a certain step, then we will be wrong in the following step, and there is no way to go back to correct it. So for example, if we are wrong at this token, the third token here, so he hit, maybe we are wrong, it's not me but it's you, right? Then we use as the input for the generation of the next token. Then maybe, I mean, if it's not me here, then the generated token for this step would be different, and we put that different word to be the input for the next step. Then of course, I mean, the wrong will be propagated to the further step, right? And in this case, we have no way to go back and to correct it, right? Is it clear for you about this 3D decoding problem? Hello, any question or is clear?
It's clear.
Okay. Okay, so let's continue. Okay, so we see the problem with the decoding here by taking the argmax. So here I introduce one way to avoid that problem by actually using the beam search in the decoding phase. Okay, so we actually want to find the target sentence Y with the length T that maximize the posterior probability. Okay, so we want to find the Y target sentence for the specific input sentence X. So it's actually, if we decompose the probability here, we can is joint probability of having Y1 first token in the condition of X, and then the probability of having the second token in the condition of having Y1 and X, and then so on, right? So it is all probability we have here. Okay, we actually, I mean, by definition, right? If we model the probability this way, we should have to compute the probability for all of Y alternative, right? And if we do that, then the complexity would be V power T, where V is the size of the vocabulary set, right? So you see, so if we, I mean, if we do, I mean, if we have to evaluate all the possibility, then, for example, in the first step here, I mean, instead of just taking the token with the highest probability to be used in the next step, we should evaluate all of the other possibility, right? And then we will end up have a lot of, I mean, a lot of cases for this. I mean, decoding, right? But the cost for doing that is so expensive, and it will cost you like V power T, where V is the size of vocabulary, because in every step you need to evaluate the V possibility. Okay, so you have the target size of T, then the number of probability would be V power T, right? So how to reduce the number of cases to be evaluated? One way to do is to leverage the beam search. So the idea of beam search is that at each decoding step, we will maintain just only K partial solution with the highest probability, and we call them as hypothesis, right? So the parameter K here is actually the beam size. Okay, so let's say that at a step instead of average or V possibility, with that average the top K hypothesis, right? So the hypothesis y1, y2, yt has a score equal to the log of its probability value. Okay, the score here is a log of the probability here, and naturally it would be translate the Zoe probability to be here is with to sum component probability. Okay, so all the score would be negative, and the higher will be the better. At the step we will keep the K hypothesis with the highest score, right? So here the beam search does not guarantee optimal solution, but is much more efficient than the brute force methods, right? Okay. Okay, so let's see the exam. Let's say we want to do the beam search with K equal to 2. First, we calculate the probability distribution of the network, and for example, starting from the start token, we have the two solution here is the one that have the highest probability, either we generate he or we generate I. Okay, and it is the score of that hypothesis, right? We keep only two highest score, two hypotheses with the highest score. So we don't average all of the probability, right? So from that, from a hypothesis, we start find the next case with the highest score, right? So for every hypothesis, we have another two highest score, another two highest score, and now we have 4 hypotheses, and we also keep only K highest hypothesis, right? So we keep the heat and the worst, right? And then we go on for each hypothesis, we go on to find the next K with the highest score, and then from that K square new hypothesis, we keep only the K highest score again, right? And then we go on, right? So if we go to if we are doing the beam search in this like in this demonstration, we can see that we don't have to evaluate all of the alternative solution, but we might have the chance to end up with the better target sentence than doing the 3D decoding, right? Okay. So at the end, the hypothesis with the highest score is a solution to be found. Okay. Okay, so for beam search, in the greedy decoding, right? Not in beam search, but in greedy decoding, the algorithm usually stop when the model generates the AND token, right? For example, start, he hit me with a pi and then okay, we found the target sentence, right? For beam search, because we have different hypotheses and the can generate the AND token at different time. Okay, so when a hypothesis generates the AND token, we call that hypothesis complete and set it aside, and we continue finding other hypotheses, right? So usually we will stop the beam search when we reach a given step T. I mean we found the solution with the specific length, right? Or when at least an complete hypothesis have been found, right? Okay. So we have several solution if we do the beam search, right? We want to choose the problem we need to do before, stop at the end of the beam search, right? The problem we have is because the way we calculate the score for hypothesis is actually, the log of the probability here. So the longer the hypothesis is, the lower the score would be, right? So the solution to address this problem is to normalize the score according to the hypothesis length. So actually, instead of that's the sum over the log probability, we can divide the sum of log probability to the second length, to the hypothesis length. Okay. Okay, so to evaluate the machine translation model, people actually using BLER score. BLER is bilingual evaluation under study. So the BLER score calculates the similarity between the translated sentence generated by the model and the label sentence created by the translator. And it measures the accuracy of n-gram with n from 1 to 4, for example. And it have the penalty for translation sentence that are too short, right? So it is the formulation for the BLER score. So for machine translation with normal test case, if we have the BLER score from 30 to 40, it means you have model that is understandable from the scale of understandable to good translation. If you have score from 40 to 50, then it could mean the model you have a high quality transformation translation. So from if you have more than 60 BLER score, then it mean is often better than human. So this is just some estimation interpretation of the BLER score. It really depends on the data set, right? So if the data set is not very enough, then the score is not reliable, right? Okay, so if we compare neural machine translation and statistical machine translation, we have some advantages of neural machine translation over statistical machine translation, so that you have better performance, more fluent translation, and better context usage, right? And it is only a single network, so it is possible to train end-to-end, and no need to optimize other independent model, so that the morphological rule or transformation rule, right? It have less human effort required and no manual feature extraction required, and no alignment vector, right? The same method is reusable for many different language pairs. The disadvantages of neural machine translation compared to statistical machine translation is the model is harder to explain, harder to debug, and it's usually considered as a black box, right? So you just know the input and then you get the output, but it will be hard for you to explain why the model come up with that translation, right? And neural machine translation is different to control. For example, it's not easy to give a rule or translation suggestion to neural machine translation, right? And to train that, you need, a big amount of data sets, right? Okay, do I have any question? If not, then I might suggest that we take a break for 5 minutes and we will continue. Okay, so let's continue. Okay, so we continue with the discussion on the attention mechanism, right? Okay, let's review a little bit about the bottleneck in the sequence to sequence model we have been studying lately in the previous slide. In the previous slide, we see the sequence to sequence model, which is a network actually consists of two components, the encoder network and then the decoder network, right? And the connection between the encoder and the decoder is the embedding information of the source sentence, which is learned when you fed the source sentence into the encoder, right? So the encoding information here should capture all the information about the source sentence, right? And you see, this is not an easy problem, right? Because the source sentence is natural language input, and the semantic of that input is so vast that it would be really hard to map, actually correctly map the high, I mean, uh, a high dimensional space into small dimensional space in the embedding representation in here, right? So that embedding information in here is actually the bottleneck in the sequence to sequence model, right? I say again, it's not easy to actually capture all of the information of the input sentence in a fixed dimension, high dimensional vector in here, right? And if you cannot capture all the information from the input sentence, then it could be very hard for the decoder to actually generate the correct output, correct target sentence corresponding to the input, right? For example, here, when you do a long sentence translation, here we have the input sentence is English one, and then we want to translate to French one. And as the input is too long, right, if you have to use a sequence to sequence model, then this input sentence again has to be mapped to the embedding representation in here. From that embedding representation in here, it will go to the decoder and generate the translated text, right? So you see, I mean, first, the embedding here is not easy to capture all the information in the output, right? And also for the decoder, by just looking into the embedding and ask the decoder to actually generate the translated text, you see it is quite a hard work for the decoder, right? As a human, when we have to translate a long sentence like this one, on the way we do the translation, we usually tend to, refer, going back to the source sentence to see what is the corresponding translation word for that specific word in the target sentence. For example, if we had to translate the first token in the target language, we usually had to refer to the first token in the source language, right? And then when we need to go on to translate the next sequence, we usually have to go back to the, this part in the input to see is corresponding translation for that token, right? Okay. So what I want to say is, the bottleneck in the sequence to sequence model had to be addressed with a novel mechanism in order to find a way to make the translation, so the decoder have more information to look at, right, instead of just looking at into the embedding, right. Okay, so here's a experiment saying the performance of the neural margin translation reduced with regard to the sentence length, right? So here you see when you increase the length of the source stack and also the length of the target sentence, you see the blur score reduce, I mean increasingly, right? So it's really saying that it will be really hard for the model to translate a long sentence, right? Okay, so to address the bottleneck of the bottleneck problem of the sequence-to-sequence model, there's an idea, and that idea named attention mechanism. Okay, the idea is a decoding step. Instead of using a instead of that, I mean, looking into the current input and then the embedding, and the hidden state of that current state, we have to use a direct connection to the encrypted network part. Okay, this is the encoder network part. Okay, sorry, I used the wrong word here. Let's make the correct encoding network part. Okay. Okay, so let's say again. So the idea of attention mechanism is to use a direct connection to the encoding network part for the computation, and from there we focus on a specific part of the source sentence, and we can somehow ignoring the irrelevant part of the input sentence, right? And it is somehow similar to the way the human do the language translation, right? So the idea of attention here is considered as one of the most influential idea in deep learning for natural language processing. And this paper discussed the attention mechanism in 2014. And this kind of attention have another name, is bundle attention, according to the name of the author of the mechanism. Right? Okay, so now let's discuss how the attention mechanism work in the sequence-to-sequence network. So you have the encoder here. Okay, it I mean it's accept the input as a normal INN and produce the embedding at the end of the encoding of the input, right? And from that embedding, we can start generate the output token for the target sentence, right? First, let's fetch the start token, okay, combined with the embedding generated from the encoder INN, right? And then we update the hidden state in the INN, in the decoder INN, right? And instead of generate the probability for the token, we now, use that output to combine with the output of the encoder INN, right? So actually we take the output of that decoder step and combine with the output in the step of the encoder, And what we want to contract here is actually the attention score, right? So we dot product the output in the encoder step with the output of the decoder step here. Okay,
thầy chưa share slide sao ạ?
Slide không chạy à?
Từ cái slide sau khi thầy sửa hình như không chạy nữa.
Okay. Các em nhìn thấy chưa?
Đã rồi.
Okay. Okay. Okay, so let me repeat again. So instead of, doing the prediction over the start token and the embedding output of the encoder INAND, here we take the decoder hidden state and we do the dot product with the output of every step in the encoder INAND in order to compute the attention score. Right, so we do the dot product for every output in the encoder at every step, right? And what we got, we name it attention score, right? And to convert to probability, we take the softmax to turn the score into a probability distribution, right? Okay, and this is a attention distribution, right? And the attention distribution saying that, okay, in order to decode that token at that step, we have to look at which part in the source sentence. In our example, here we want to decode the first token in the target sentence, and what we see here saying that, okay, to decode that token, we need to take closely look and focus on the token at the beginning of the source sentence, right? Okay. Okay, so this is actually the attention output, and the attention output, we use the attention distribution to take a the sum of the encoder hidden encoder hidden state, and the attention output here will mostly contain the information, the hidden state that receive higher attention, right? Okay, so we combine the attention output with the output of the decoder at that step, and we actually doing the concatenation, right? And then we use that output to predict the token at that specific step, right? So again, for the next token, right, we also do the dot product of the decoder hidden state with the output of the encoder and at every step to get the attention score, and we do the softmax, we get the attention distribution, and we do the weighted sum of the attention distribution with the output with the hidden state of the encoder at every step to get the attention output, and then again we do the concatenation with the output of the decoder, and then from that we predict the next token. Okay, and then go on. Okay, so that was the idea of the attention mechanism, right? From the explanation, it doesn't look to be complicated, but the the idea was so innovative that it is considered as one of the most popular, not popular, but it's the most impactful, influential idea in the deep learning for NLP. Okay, so if we want to discuss the formulation for the attention mechanism, we can we can discuss the following. We have encoder hidden state denoted as the S1, S2, Sn, right? On step T, we have the decoder hidden state St. Okay, so we get the attention score ET for this step equal to this formulation. So actually we multiply the St with every hidden state at every step of the encoder, right? So then we take the softmax to get the attention distribution alpha T, okay? And then we do a weighted sum of the encoder hidden state to get the attention output, right? So that with sum of alpha T at, okay? And finally, we concatenate the attention output with the decoder hidden state St and process at the non-attention second-to-second model. From that, we can do, softmax to get the predicted token of that specific step. Okay, so the attention mechanism significantly improve the neural machine translation performance. It is very useful to allow decoder to focus on a certain part of the source. The attention actually solves the bottleneck problem in the second-to-second model instead of, predicting the token just by the input token and then the hidden state. We now allow the decoding to we allow the decoder to also look at the embedding to look at the hidden state of the encoder network with a specific distribution with the focus on a specific part of the input segment. Okay, so now we no more having bottleneck. Okay. The attention have with a vanishing gradient problem. So now we have the connection from the decoder to the encoder. So we provide shortcut to faraway states, right? And the attention also provides some interpretability. By inspecting the attention distribution, we can see what the decoder was focusing on when it decoded the token of a specific stack. And then from that, we get the alignment for free, right? Okay, so that was the idea about the attention mechanism. For reference, you can take a look into the CS224N class at Stanford University and CS231 and also at Stanford University. Do I have any question? Okay, so if you have no question, then I suggest you open the notebook, the lab that I said to you in the previous class, and then in that notebook you see the notebook corresponding to the neural machine translation with attention mechanism, and take a look into that notebook and try to understand step by step and doing the exercise. Do you understand my point? Hello. Okay, so take a look into the notebook, and then we will come back in like let's say 20 minutes to discuss how it's going. Okay. Okay, so let's continue. How's this going on the side? Anybody can share the progress on the notebook? Hoàng Thiện Tâm, can you discuss a little bit on the notebook?
I have just read through the notebook, but it's a bit hard to understand for me, so I still need more time. Sorry, teacher.
Okay. Okay, so D2L library, such a library associated to the D2L book. So D2L book, you can D2L.ai. So it's very popular and a famous book on learning deep learning. Okay, if you go into that website, you can see a lot of material with a lot of notebooks associated with it. You can practice in PyTorch, TensorFlow, and AmicNet. Okay. Okay, Nguyễn Tuấn Dũng, can you say a little bit on the progress?
I haven't really. It is the notebook is. I don't really know how to pre-process data.
You don't know how to what?
I'm still working. Yeah, I'm a little bit confused about the pre-processing since I'm not familiar with this type of stuff, so I'm still reading through it.
You are not familiar with PyTorch?
I'm not familiar with. Yeah, I'm not familiar with PyTorch and the data pre-processing of these types of data.
That's not what I want to hear, because you know we are at the at the ending of the of the course, right? So I expect that after the course you should know how to program in Python, in TensorFlow, or whatever, because you need to do the milestone project. Is that correct?
Yes, but yeah, I'm more confused about the pre-processing rather than the model itself.
In which notebook? Can you show the screen?
Yes. So, just wait a minute. Excuse me, when you said we should read a notebook, which notebook do you mean? I was reading image captioning notebooks first.
Okay, so I think that you didn't pay attention to the course for today. It's so sad to hear that. So let's ask the other student. Hoàng Nguyễn Minh Nhật, Hoàng Nguyễn Minh Nhật. Are you there? Okay, so yeah, it is too bad that you are somehow busy with something else and not working on the and the requirement test. So I know what to do with you, but maybe in the next week we will stop the lesson a little bit and try to discuss on the progress on the milestone project. I hope that at that time you already working on the milestone project and you have something to say, right? In the previous discussion on the milestone project, you guys didn't do anything besides just choosing the topic, so we cannot discuss, right? So I hope that for the next week it could be different. Otherwise, I hope that I will not be able to give you guys good note for the milestone project, because this is something that you have to done throughout the course from the beginning to the end, not a few weeks in the end, right? Any question for today's lesson? Hello. Okay, so then we can stop here. Remember that for the next week, we will have discussion on the milestone project. So you guys have to do something. Otherwise, I will give you the grade for that, preparation. Okay, understandable? Hello, you guys.
I have a question.
Yes.
That is related to the syllabus of this course. Do we have a lecture dedicated to generative models?
Yes, there's something at the end of the course.
Okay. Thank you.
Okay, so thank you and bye bye. See you in the next week.